Welcome everyone, my name is Mohamed Maho and I am a PhD student at TU Braunschweig in Germany. And today I would like to present to you SGXoMeter, a benchmarking framework dedicated for Intel SGX. So without further ado, let's start. Trusted execution environments are gaining a lot of interest lately and their development is rapidly changing by time. They offer confidentiality and integrity against a strong threat model, such as compromise, hypervisor, or operating system. They also provide protection against malicious and untrusted cloud providers. These hardware-based technologies are developed by prominent CPU companies such as Intel and AMD. And for the Intel side, we have Intel SGX, which stands for Software Guard Extensions, and AMD SEV, which stands for Secured Encrypted Virtualization. These technologies have found usage in commercial secure clouds such as Microsoft Azure, which is based on Intel SGX, and Google Confidential Clouds, which uses AMD SEV. The question here, however, is how do these frequent changes and enhancements on these technology really affect the performance? So, since we are targeting Intel SGX, let's have a brief introduction into it. Intel SGX is an extension of the x86 instruction set. The newly added instructions create the trusted execution environments, the so-called enclaves. These enclaves are isolated memory regions and stored in an area called the enclave page cache, the EPC. Enclaves are part of the application and they contain the sensitive code and data. They can be accessed by special instructions. However, in order to avoid working with the cumbersome instructions, Intel also provided a software development kit which has wrapper codes for these instructions to enter and exit the enclaves, hence the equal and on-call. Increasing the security comes most of the time at the cost of the performance. And there's always this trade-off. Therefore, multiple researchers have conducted multiple experiments in order to determine the factors behind the performance overhead. And for the first factor is the enclave size limitation. Intel SGX CPUs currently come by design with a limited EPC size. Initially it was 128 and recently it is extended to 256 megabyte, from which only 93 and or 188 megabyte usable for the enclaves. Researchers or research papers such as SecureKeeper and SCONE have done experiments upon exceeding these EPC limitations and have observed performance overhead of up to 1,000 times the execution before exceeding that limitation. Another factor is the enclave transitions. The equals and o-calls, what appears to be normal function calls. However, in the background, there's more happening, such as security checks, buffer copies, and so on. And in hot cold paper, the researchers did micro benchmarks in order to measure the performance overhead compared to the normal function call, to the native function call, and they have also observed a huge performance overhead. However, there are also other factors that can have an impact on the performance, which is one of them the evolution of this technology itself. Intel SGX CPUs offer a software layer which can be updated by microcodes. These microcodes can mitigate, or some of them mitigate, some side channel attacks such as Spectre and Foreshadow. These mitigations also increase the performance overhead, which is measured in SGX Perf paper, where they have also observed that the performance overhead after applying these mitigations increases the enclave transitions of almost triples the performance of these. And there are also other papers that contribute with mitigations against control channel attacks, such as mitigations for page fault attacks or band shadowing attacks, and they have conducted their own benchmarks in order to measure their performance overhead for their solution. And last but not least, since the T is evolving, the development of the SGX SDK is also progressing as well with it, so they add enhancements and mitigations which also might or do have impact on the performance. But what we have seen till now, these are most of them are micro benchmarks, or the other papers doing their own benchmark to measure their solution. So there is no widely used application benchmark dedicated for Intel SGX. So we identified this problem and did in our research for existing benchmark frameworks for Intel SGX, and to our knowledge we only found one, which is SGXNbench, and we decided to analyze its suitability and as an SGX benchmark and highlight existing flaws. Upon that, we developed our own benchmark tool, SGXoMeter, which is extensible and easy to use. It provides a set of SGX suitable benchmark applications and allows you to reproduce and compare your research results. The contents of this presentation is as follows. We will start with the brief analysis and evaluation of SGXNbench, and then we'll present to you SGXoMeter with its workflow and architecture, followed by a performance overhead evaluation of 2 different SGX SDK while using SGXoMeter, and at the end we will give you an insight of the upcoming plans for SGX for this framework. SGXNbench, in a nutshell, it's a neat part of NbenchByte. Originally, the NbenchByte benchmark framework is developed in the mid-90s. It does CPU, FPU, and memory-heavy speed benchmarks. So it's in total, it's a self-contained benchmark framework written in C and single-threaded. And there's researchers from SGX Lab who are all implemented an SGX part version of it in order to measure their performance overhead by applying their mitigations against page fault attacks. They open sourced this part, and it was indeed used in other research papers, such as mitigating branch shadowing attacks. And also other papers mentioned that they did a part themselves of the same benchmark tool. So let's take a look at the workflow analysis and our evaluation regarding the usability of this, like while looking at the workflow. The benchmark starts like this. It accepts optionally a configuration file, which will be parsed and replies to default values if it was given. Otherwise, if it's not given, then the hard-coded default values of the developers will be taken. Since there is no documentation how to use the configuration file, or if there is a configuration file whatsoever, other users, like third-party users that would like to use this framework, would use it out of the box. So they will most probably fall into the unknown hard-coded values of the application, which might be not very useful for them. The next step is the preparation step. It's where the enclave is created with the needed buffers, with the based on the default values that are chosen in the previous step, and then the benchmark loop will start. Here we noticed that there is no warm-up phase. This warm-up phase basically we consider it important, especially for memory-heavy benchmarks, in order to exclude the outliers generated from cold cache. And especially the case here, since they do at most 30 iterations for each benchmark. So we have a small sample set for each benchmark, therefore a warm-up phase could be beneficial. At the end, we have here, the results will be outputted in textual form, but there is no sensible baseline to compare with. They do not offer a baseline for comparison reasons. The output, here's a snapshot how the output could look like. Here in this column, you'll see the performance of the current machine for the 10 benchmarks that are run. And the third and fourth column, it's hard-coded values directly taken from the original NbenchByte. We analyze the SGX suitability of these benchmarks regarding like if they are suitable, and we consider a subset of them is suitable for SGX since they operate on security-sensitive data such as cryptographic benchmarks and neural network and so on. But the rest are arguable and use case dependent if you really need to do these other benchmarks inside the enclave or not. Another thing that we notice is that the enclave transitions are included in their measurements, which in some cases really not reasonable, such as in bit filled, where they do where the benchmark does 1 bit flip, 2 bit flip, and 3 bit flip, and so on incrementally. and these operations basically doesn't take as much as the enclave transition itself. So the measured value here in this case would be not sensible. And the last question is if the generated results are reliable for other users. Of course, they were most probably reliable for the original writers, but for different users, it stays questionable or arguable. In this case, we identified the need for a dedicated application benchmark framework for Intel SGX in order to reproduce the results as well as compare to other research papers in case they both do the same mitigations against the same attack. So here comes SGXoMeter into game, and it's a benchmark framework dedicated for Intel SGX applications that uses the Intel SGX currently. It's an extensible framework where everything is a module, which means the benchmark that we built in, they are modules. They can be selected and unselected at compile time. Currently we do not consider the enclave transitions during the benchmark, which means we purely measure the performance inside the enclave. And it offers a user-friendly interface, so it's easy to use. The framework structure is as follows, can be categorized into 3 levels. We use CMake as a build system, which allows us to categorize it into this kind of classification. So the outermost level, the level 1, there the environment variables are configured and the needed dependencies for the modules will be installed. Then we'll transfer to the second level where the modules are configured. Here you as a user will have the GUI option as well, where you select which modules you want to benchmark, and upon selection you will get another list for configuration variables for this module. Once finished comes the last step in the last level where the binaries are generated. We generate up to three binaries. One binary is the baseline, which is completely without SGX primitives, and 2 SGX binaries, once in hardware mode and once in simulation mode. All these binaries share the same source files, which means they run the same source files for the benchmark tests. And with minor changes regarding the SGX primitives in the case of the baseline, of course. The workflow is as follows. At the start, there is an input parsing phase, which means the default configuration values can also be configured at runtime, not only at the compilation time as we saw earlier. Afterwards, the 2 threads will be created, the benchmark thread and the measurement thread. The benchmark thread will enter the enclave and does the pre-benchmark or pre-adjustment step, where the enclave will be configured with the predefined values in the previous step. Afterwards, these 2 threads will halt and wait for a signal from the main thread. Once given, the benchmark will be initiated. The benchmark thread will enter the benchmark loop and increment counter after each successful iteration. Meanwhile, the measurement thread will enter 2 phases, the warm-up phase and then the runtime phase. Upon finishing these 2 phases, it will log the current value of this counter, which is incremented, and then it will signal the benchmark thread to abort and enter the post-benchmark phase. Here it will clean the buffers used for the benchmark, and then they will both meet in this intersection point. In this point, the main thread will take a look into the module selection list if there are other modules to benchmark. If that's the case, the process will repeat from the start again for the next module. In case all modules are tested, then the logged files will be outputted and with their corresponding statistics. And in the last phase, of course, the benchmark will be cleanly terminated. So basically, this is very briefly how it works. And now we come to the implemented benchmark modules. As we mentioned, we offer a set of SGX-suitable benchmark applications. And one of them is Seek. Seek is an open source library for DNA RNA pattern matching algorithm. It does CPU and memory heavy calculation on given DNA sequences. So since it operates on DNA sequences, we consider this as security sensitive data, and therefore we ported it first into SGX and then added it as a module to our SGXoMeter benchmark framework. We also ported or implemented other benchmark modules, mainly based on the Intel SGX SSL library, which itself based on OpenSSL. These modules include RSA modules that like key generation, encryption, decryption of different sizes of strings and messages, and signing and verification. Also, we also have a charm module and other cryptographic modules such Diffie-Hellman, elliptic curve, and so on. In total, we offer 15 modules. We are not going to go into details for each one of them because of the time limitations. So we will stick to what we have now. For the evaluation, we evaluated, as I said, first two SGX SDK versions, an old one, 2.7, and one of the recent new ones, 2.12. We tested it or evaluated based on the three binaries, the baseline and SGX in hardware and simulation mode. We have chosen 10 seconds for the warm-up and 60 seconds for the runtime, and they all run under the same system specifications. They all have the same kernel version, the same CPU microcode, same SGX driver, and the same CPU. So starting with DNA RNA pattern matching algorithm, here we can see for small workload or small DNA sequences, the performance overhead of the newer SDK have dropped up to 10 times compared to the baseline. Whereas the older version of the SDK, 2.7, only drops to 1.3 times compared to the baseline. This means almost up to 8%. The newer SDK is almost 8 times slower than the older ones. In order to verify this finding, we have done, of course, other benchmarks, such as benchmarking the Intel SGX SSL SHA-256. And we have witnessed the same performance overhead pattern for small workload sizes, as we can see here, where the newer SGX SDK version 2.12 has the performance overhead from SGX 2.12 has almost doubled the older ones. So in order to also more verify these findings, we have reproduced the same or similar results on 3 different machines and seen the same behavior. So now we'll give you a brief idea of what we are planning to do next with the framework. We want to implement more benchmark modules in order to cover a wide variety of use cases, such as porting specific benchmarks, which we consider SGX suitable from SGX NBench, and compare the generated results from our framework against theirs. We want to implement other modules based for different hardware accelerated cryptographic algorithms from other libraries, such as libsodium and so on. We will also look into the feasibility of supporting applications based on other frameworks, such as OpenEnclave and Graphene SGX, and see if we are able to benchmark such applications. And of course, last but not least, we want to add extra features and better usability. One of these features, like opting in the enclave transitions in the measurements, as the case in SGX NBench, and see what the performance overhead there will be. And a usability feature such as setting the enclave's configuration from the GUI and automatically generates the corresponding enclave configuration file. So we have come to the end of this presentation. In summary, we have identified here the need for a practical and reliable SGX benchmark tool dedicated for Intel SGX applications. And we have taken a look what, to our knowledge, the only SGX application benchmark framework, and have seen some of the drawbacks. And then we presented SGXoMeter, which is high modular, easy to use, reproduces the results, and lastly, it's open sourced. So feel free to use it or contribute to it if you want. and please consider using it for your future SGX research in order to reproduce your results and compare them to each other. So at that point, thank you all for your attention and stay healthy. Goodbye.